Hey students, welcome back. This is Torres, Elbow Bump. How are you? Are you doing okay? How's your family? Are they okay? Remember, if you need anything, please send me an email so that I can try to help any way I can. So lucky you, you get to hear my voice for another lecture. But the best part is we will be interpreting the line of best fit. Yay! So what is the line of best fit? Well, trends on a scatter plot can be represented by a trend line. Another way to say trend line is the line of best fit. The line gives insight into the relationship between the independent and dependent variables. This may give you a basis to predict what data might be for values that weren't in your data set. We're going to be talking about lines. So one of the reasons why I created that little mini review, which I'll link up here, was for us to kind of do a little refresher that lines can be described by using the equation of a line. The equation of a line is y equals mx plus b, where m is the rise over the run, and b is the place where the line intersects with the y-axis. Now, we've already discussed this in the past, but again, this is just a quick little refresher. When graphing, we have our x-axis and our y-axis. The independent variable goes on the x-axis and the dependent variable goes on the y-axis. This information, independent, dependent, and the information about the slope, rise over the run, and the y-intercept will give us information about any relationships that might be happening with the data of our scatter plot. One thing that you always want to remember is that our purpose in statistics is to take a sample to make an inference about the larger population. So when we're working with the line of best fit, this line of best fit is being created with data that we took from our sample, right? We can't use the whole population. So the slope and the y-intercept are the unknown population parameters that are estimated from the data. So we're still trying to use our scatter plot to make inferences about the population. So let's talk about this in a little bit more detail. So here I have two scatter plots, right? I have my independent variable and my dependent variable, independent variable and dependent variable. And here there's a bunch of points that have been plotted. Okay, let's start talking about this scatter plot first. So here you can see that there were all these points plotted. In this class, we just work with linear shapes. So it has a linear shape. It's a positive trend. And I would say this is moderately weak. It's not real weak where things are really kind of blown out too much. But, you know, it looks good. You can definitely tell that it's a positive trend. So what they've done with the line of best fit is they try to draw it through the trend to the point where they are trying to minimize the residuals. Residuals are the distance from each one of these points to the line of best fit. If I were looking above the trend line, these red ones are my residuals. And if I were looking below the trend line, these black lines are my residuals. The same thing is happening here. The scatter plot here is linear. It has a negative trend, and I would consider this pretty strong. You've got some points that are right on the line, some that are very close and through here. So this is looking like a strong relationship between the independent and dependent variable. Here, the same thing is happening. These lines, the red lines above the line of best fit and the little black lines below the line of best fit are the residuals. So what the line of best fit does, and we're going to just be using technology for this, is it draws the line through the scatter plot in the direction of a trend in a way to minimize these distances. So the absolutely least amount of distances are being considered in the calculation. So again, that is the scatter plot. These things flying in are the residuals. Scatterplot, residuals. The idea is to minimize the residuals or lessen the residuals as much as possible when creating the line of best fit. So we can say the line of best fit is a line that minimizes the sum of squared differences between the points and the line. In other words, the residuals are lessened as much as mathematically possible. And since it's a line, the equation of the line, y equals mx plus b, will describe it. So with a line and this formula, we have a way to sort of merge those two ideas together to be able to gain insight on what's happening between the two variables. Okay, so I moved us over to Xiteboard, and don't forget that I will link the Xiteboard in the description box. And I have gone ahead and put this graph into it, and this is a scatter plot. This is looking at the independent variable ads, like the ads that you would see like on YouTube or the ones that people pay for on Instagram, commercials, magazine ads, whatever. And then on the y-axis, we have the dependent variable revenue. And revenue is how much you earn from a sale. So I'm going to go ahead and write that out here just so that we can keep it all straight. So the x-axis is the independent variable. And that, in this case, that is ads. And the y is the dependent. And in this case, it's revenue. Okay. All right. So here a scatter plot has been made. Maybe stores or influencers or whatever companies went ahead and bought ads, and they wanted to see how much money that they could attribute to the ads itself. So here they've plotted out the points. And just as an aside, see how these points are all lined up like in a column? So this happens when you have discrete variables. Okay, so anything that's discrete. Here we have like $1, $2, $3, $4. It's not like they had $2.52. If it was something that was more continuous, we would see more of what you're used to in seeing a scatter plot. So this was made with discrete data. You won't be tested on that, but I just thought I would point it out because some of you might think that looks weird, but it's fine. And here the computer has gone ahead and created the line of best fit. Remember, the line of best fit minimizes the residuals, and went ahead and calculated the equation of a line. So I'm going to go ahead and go up here and match this up. So usually we see, usually we see y equals mx plus b, but in stats, they love to mix it up, and so they usually post it as b plus mx. Okay, so what have they done here? Here, instead of x, they wrote add, and here, instead of y, they wrote revenue. Okay, predicted revenue. So we had already established the independent and dependent variable. Now let's look at what these numbers mean. Well, I also know that my slope is going to be this number in front of the independent variable. So my slope is 1.2. And my y-intercept, which is in this place right here, is 1.8. Okay, great. So this has given me a lot of information. The equation of the line, the scatter plot. Just as a quick little review, let's see if we can describe it. So we've got shape. In this class, it's only one shape, linear. We've got trend, positive, negative, or none. This is positive. And we also have strength. And I would say that this is moderate, maybe. Okay, so we've gone ahead and described it. Looks good. Now we don't have the correlation coefficient here, but that's okay. We don't really need it right now. Okay, so let's interpret this. So this M, right, my slope, we talked about how that is the rise over the run. And we know that the slope is 1.2. And we can write that as 1.2 over 1. So what is this saying? Our rise is revenue, and our run is ads. So for every $1 they spend on ads, they can expect $1.2 in revenue. So now, is this always going to happen? No, we're using this model of this scatter plot and the trend that it's showing in order to make a prediction about the population. Sometimes, as you can see, some people make, more than $1.20 in revenue when they spend $1. We don't know. This is an overall average and what we would expect to see in the population. I'm going to scooch this up. The other thing we can talk about is the Y-intercept. The Y-intercept in this example is 1.8. So what does this mean? It means that in this scenario, if they spent no money on ads, then they would expect a revenue of $1.80. Right? So spending no money, you're at $1.80 revenue, and for every dollar that you spend, it increases by $1.20. So if you spend $1, you can expect to get $3 in revenue, right? 180 plus 120. And it just keeps increasing at this regular rate of 120, 120, 120 for every dollar that you spend. You can find this explanation in the Google Slides as well. I have provided the link to the Google Slides in the description box below. And this just has the same exact information that we discussed on Ziteboard. Now, there are times where the Y-intercept is nonsensical, and this is an example. So this says, a sample of high school freshmen and sophomores resulted in a regression equation that relates age to height in inches. So here is my graph. My age is going on the x-axis, and my height is going on the y-axis. So I can say x is my age, and that's the independent variable, and y is height, and that's the dependent variable. Okay, very good. And I also have information about the slope. The slope is positive 4.9. It's really steep. And I also have information about the y-intercept, which is negative 9.2. All right, so I'm going to need a negative line to kind of show up here too. Awesome. Okay, so this line of regression is going to cross the y-axis somewhere down here. I'm just going to try to draw a line as best I can, like this. Okay. All right, so it crosses down here at negative 9.2 inches. All right. All right, so let's look at the slope first. For the slope, I can say that I have this slope, right? This is my rise, and this is my run. So for every 1 year of age, a student can expect to grow 4.9 inches. So that would be my interpretation. For every increase of 1 year, a student can expect to grow 4.9 inches, and let's just put on average, because this is an average trend line, right? The trend line is the average of the scatter plot. So that hasn't changed since the last example. But now let's look at the y-intercept. The y-intercept is saying negative 9.2 inches. Well, you can't be negative inches tall. You can't like grow into the ground. You can't go negative. So in this case, it's not sensical. You can't say when a student is 0 years old, they are negative 9.2 inches, right? So it really starts at a certain point, and then it increases from there at the slope of 4.9 inches per year. So in this situation, we can just say that the y-intercept is not able to be interpreted. Okay, that's all you have to say. It's uninterpretable. Again, there is a summary of what we just did in Xiteboard on the Google Slides that I have linked in the description box below. So what's the big idea? Today's big idea is that the line of best fit is the line which is created by minimizing the residuals, and it describes the trend of the data. The equation that describes the line of best fit can be interpreted to describe the scenario and context. So that's it for today. With that said, don't forget to check your emails, check Blackboard, do your homework, and subscribe to this channel. Even better, hit that notification bell so you know when there are new videos for this course. Okay, this is your teacher Torres saying stay safe, and I will be waiting to give you a virtual elbow bump in the next video. Ciao!